everyone, thanks so much for being here today. I'm Myungji-go from Gangwon National University, and I'm excited to share our work, visual and auditory feedback of vibration and particle effects for enhancing pseudo-haptic button interaction in VR. So let's start with some background. VR has grown rapidly in games, training, and education. In VR, middle hand gestures provide natural interaction with virtual objects without using any physical devices. But the problem is these gestures don't give haptic feedback, so the experience feels less real and immersive. To solve this, people tried devices like haptic thimble, haptomime, and physical props. But each of these has big limitations. They are expensive, complicated, and often uncomfortable. That's why we look at pseudo-haptics. It creates a touch illusion through vision and audition using the brain's natural sensory integration. It's a practical and accessible alternative for VR. Now let's move to related work. Previous studies showed pseudo-haptics can improve VR button interactions. On the left, pseudo-haptic menus were preferred over simple menus. In the middle, 3D lookalike buttons with haptic feedback made the process smoother. And on the right, combining visual and auditory feedback created vibratactile illusions. One important study by Kim and Xiang tested the heat effect, which combined visual vibration and particle effects, and found it very effective. But they didn't separate the two, so we don't know which mattered more. And this is the gap that we focus on. Previous studies used combined cues without a clear multimodal design and didn't isolate visual vibration and particle effects. So in our study, we isolate these subcomponents, evaluate their individual and combined impacts, and tested them in middle button interactions using only visual and auditory cues. Now let me explain our methods. We recruited 36 participants, mostly live VR users or right-handed. We used a mixed design. One group had no auditory feedback, while the other group received it. Each participant experienced 27 button conditions with different vibration parameters and particle effects. When auditory feedback was present, we used a smartphone vibration sound for pitch-matched frequency and volume-matched amplitude. Let me briefly show you how the buttons looked in our experiment. Here's on 3 examples with different vibration parameters and particle settings. You can also find their specific parameters listed below each video. The procedure had 4 steps: instruction, a short pre-survey about VR experience and the main experiment, and finally an interview. After each press, participants answered 2 surveys: a subjective evaluation questionnaire measuring haptic illusion, embodiment, sense of reality, presence, spatio-temporal perception, and satisfaction, and the UQS, which evaluated overall user experience, including both pragmatic and hedonic quality. We ran 2 rounds of analysis. First, we tested the presence of vibration, auditory feedback, and particle effects. Second, detailed parameters of vibration, frequency, amplitude, and duration with auditory feedback and particle effects. Now the results. Visual vibration improved haptic illusion, sense of reality, spatio-temporal perception, and satisfaction. Auditory feedback had smaller effects, but still improved timing. Particles were strongest, boosting almost all measures. Smooth particles work best, while big ones sometimes reduced consistency. UQS results showed the same. Visual vibration and particle effects improve the both pragmatic and hedonic quality, while auditory mainly improved pragmatic quality. Looking at interactions showed that adding one cue to no feedback made a big difference, but adding more cues after that gave smaller gains. Now moving on to the second part of our analysis, the detailed parameters of vibration frequency made almost no difference. Amplitude showed that bigger motion felt stronger. Duration was the most critical. A longer vibration, 0.3 seconds, consistently improved everything compared to 0.1. UKS showed the same thing. Duration made the biggest difference. So what does this all mean? Particle effects gave the biggest boost. Visual vibration enhanced haptic illusion and realism. Auditory feedback mainly helped timing. And among the vibration parameters, duration was the key factor. From interviews, participants said the visual vibration made practice feel more real, and some even said almost like real tactile contact. Sparkle-like particles boosted impact and enjoyment, but big ones without matching cues felt incoherent. Click sounds improved timing and realism, and louder or lower pitched sounds felt conveniencing. For parameters, longer duration was clearly stronger, higher amplitude sometimes too forceful, and the frequency differences were barely noticeable. Based on these findings, we suggest some design implications. First, leverage multimodality. Combined cues feel richer than one. Second, use particles wisely. If they are too big or out of sync, they break the illusion. Third, optimize the vibration duration. Too short feels weak, while slightly longer gives clear confirmation. And finally, enable personalization. Since people differ, giving options improves the experience. Our study had a few limits. First, we tested only a limited parameter range. Second, auditory feedback had constraints. Pitch and volume were not treated separately, and we used a smartphone vibration sound. Third, we didn't use objective performance metrics. And finally, there was a cross-modality issue. Visual and auditory cues weren't intensely matched, so we can't say which one is stronger. So for future work, we plan to explore broader parameters, refine audio design, and include objective metrics. To wrap up, our study shows that multimodal stochastic cues can really enhance user experience in VR button interactions. Particle effects had the strongest impact, followed by visual vibration. Among the vibration parameters, duration was the most critical. We also found that keeping cues consistent is vital because mismatched cues lower the quality. And since users vary, adaptive or personalized feedback is needed. That's the end of my talk. Thank you very much for your attention.
Thank you very much. You didn't, let me give a chance to ring the bell. So means that we have a lot of time for question and answer. Is there any question from the stage? No, sorry, from audiences. Here's one hand.
Well, hello, my name is Song Min from KAIST. I believe that these kind of visual cues have greater effect if it provides better presence. And also in the picture you showed me, I saw there was a hand thing. I believe it gave some amount of embodiment to the user because it's a human interaction. So embodiment has also greater effects. But maybe if the shape of the hand would resemble the participant, would it have some effects? I'm just curious. I'm just curious about the effect of embodiment and presence in this kind of interactions. Thank you.
It was mentioned that you picked a small set of different parameter values. And so the question is, that was for the formal study. Did you also do a pilot study to try to figure out which of the parameter values you should pick? Trying maybe ones that were higher frequency or lower frequency or louder or softer or whatever.
The vibration parameter levels were determined based on prior research, design guidelines, and pilot testing. For frequency and amplitude, we adopt 40 Hz and 1 centimeter as upper bounds based on prior study, and identified 10 Hz and 0.5 centimeter as perceptible lower bounds through internal testing. For duration, we refer to user experience animation guidelines.
Okay, thank you.
So one of the most critical, highly related previous literature was the right one, the visual plus auditory feedback done by Kurzweig et al., like vibro illusion. And some of the parameters we directly adapted from those studies, and we also did several series of pilot tests to ensure that what is the optimal level to investigate.
We still have 1 minute for a quick question. Yep, there's a hand.
Thank you for your presentation. I'm Sung Shin from KAIST, and just a brief question, just a curiosity. Do you have any ideas on treating multiple buttons with different multisensory inputs so that users can feel more diverse pseudo-haptic results, so that user can feel more immersed experience in that kind of pressing buttons? Both would be okay.
Mm.
Just a curiosity. I see. Thank you.
Okay.
Hello everyone, my name is Minju Baek. I'm a PhD student from KAIST. Today I'm excited to present our paper titled is Visual Tactile Feedback with Hand Outline Style for Modulating Affective Roughness Perception. So VR is a powerful medium for studying emotion, allowing users to safely experience feeling like relaxation, anxiety, or excitement in controlled setting. So how can we measure emotion? We use the circumflex model of affect, which defines two-dimensional arousal intensity and balance positive or negative. Many VR studies use this model for passive experience like scene viewing or social touch, but emotional response during active object interaction remains underexplored. When we touch an object, we feel its texture, the smooth and the rough through our hands. This multisensory experience can even evoke emotion. For example, the same object, a towel, can feel pleasant when dry, but unpleasant when wet. But when we touch virtual object, what do we feel? There's no object, no tactile feedback. So in our work, we express roughness using fingertip vibration enhanced by affective visual cue to shape emotional perception. Previous studies show that vibration parameters such as frequency and intensity can reproduce different levels of surface roughness. So we can map haptic roughness through vibrotactile feedback. Vibrotactile roughness is also linked to emotion. For example, increasing roughness raise arousal and lower balance. Although this is a unimodal haptic effect, we extended it to a multimodal perspective by combining vibrotactile and visual cue to enhance emotional expression beyond haptic alone. Prior studies show that visual cue and relevant motion can modulate perceived roughness, even without changing tactile input. Vibrotactile stimuli link with visual features like color, while color and motion evoke emotion, showing that touch, vision, and emotion work closely together. Visual cue in VR can modulate both tactile and affective perception. So we designed visual tactile feedback combining haptic and visual cue to modulate affective roughness during hand-object interaction. Our key concept introduced a hand outline approach using the avatar hand as an expressive affective channel. We designed a multimodal system that combines vision and touch for expressive emotional feedback. So we explore a hand-centered design space. We express roughness using fingertip vibration. For the roughness design, we use vibrotactile stimuli at the fingertip to intensity and for duration. For the affective roughness design, we focus on visual feedback around the hand during interaction with virtual objects. We ask, where should this feedback appear? Possible targets are the object surface or hand appearance. But we chose the hand outline because it's subtle, always visible, and naturally convey affective feedback. Next, how can we modulate the outline? We use two affective visual parameter line style and color. Curved lines evoke positive, sharp line negative feelings, and faster motion add tension, and color map to balance and arousal. Finally, we implemented 6 line styles and 4 colors, synchronized with vibrotactile feedback in Unity to explore how this combination influence affective roughness perception. We implemented outline with shader-based vertex displacement in Unity, adding slow and fast motion for real-time emotional modulation. So this is our proposed system combining vibrotactile and visual hand outline feedback to express both roughness and emotion in VR. Before the main study, we ran a preliminary test with the Tech Glove DK2 to see if vibration could represent roughness. It used 2 intensity level and 4 pulse duration. 10 participants rated roughness on a 1 to 100 scale and arousal balance using SAM. We classify 8 vibration patterns into 3 roughness level: low, medium, and high. Higher intensity, felt rougher, more arousing, and lower in balance. This experiment verified that vibration can represent roughness. We selected 3 represented levels, and interestingly, each roughness level showed a distinct affective range. We used them as the 3 representative haptic conditions in the main study. Now let me explain the main study. Our goal was to examine how visual feedback, line style, and color, and haptic feedback together shape affective responses and perceived roughness. We conducted 2 separate conditions: haptic line style and haptic color, to avoid overlapping visual cue. The dependent variables were balance, arousal, perceived roughness. For the haptic design, we used the 3 representative stimuli selected from the preliminary study, each roughness level. For visual feedback, we used 6 line style and 4 color as shown earlier. Each condition was repeated 3 times in a random order, and we recruited 24 new participants for the main study. When participants touched the object, haptic and visual cue were presented together for up to 3 seconds. Result for 2 conditions we measure by balance, arousal, and roughness. The blue box shows significant effects. There were no interaction effects. This means independent modality effect. Visual and haptic cue acted independently. Haptic feedback consistently influenced all measures, as higher roughness, lower balance, increased arousal, and felt rougher. Visual types show different effects. Line style influenced all measures, while color affected only balance. Designer can selectively use them to achieve specific emotional goals. Let me briefly show the result for haptic line style. For balance, stronger haptic, sharp line, lower balance. For arousal, stronger haptic and sharp line, increase arousal, amplifying emotional intensity. For roughness, stronger haptic, sharp line make surface feel rougher. Moving on to haptic color. For balance, stronger haptic red color made it more negative. For arousal, only stronger haptic increased arousal. Color was not significant. For roughness, only stronger haptic increased roughness. Color had no effect. In the arousal balance space, visual type modulate emotional perception. You can see this graph. Haptic mainly drove perception. Higher roughness increased perceived roughness, and higher roughness increased arousal and decreased balance. In haptic line style, sharp line increased arousal, and while in haptic color, arousal showed no effect. For arousal, the visual effect stays within the haptic gap, so to modulate arousal, you need to adjust haptic intensity. For balance, line style shift is from none, sharp negative, some positive, while clearly cause negative balance. For balance, line style shift is from none, some negative, some positive, while else clearly cause negative balance. As haptic intensity decrease, balance variation increase, and at low level, it even reached the mid-level balance range. Sharp line and red color both show negative balance. Here our design strategy. Using a commercial haptic glove, our system enable expressive emotional interaction even under hardware limit. Combine modality, we suggest use haptic to control a larger visual to fine-tune balance. In gaming or training, designer can use sharp visual and red tones to amplify tension. In therapy or relaxation, avoid negative cue to stay balanced. We applied this concept in gaming, product interaction, and adaptive feedback, showing that the same object can feel different depending on visual haptic context. In summary, we propose hand-centered visual tactile feedback show that visual haptic cues have stronger emotional impact than haptic alone, and demonstrate the hand outline as an expressive, affective channel. Future work will explore visual combinations such as color and line style, diverse users, and spatial context for more embodied emotional interaction. As shown in this work, multisensory feedback design is not just about enhancing a single sense, it's about creating new experience, like color blending into a new hue. I believe multimodal feedback opens new possibility for interactive experience. Thank you for listening.
Thank you very much. Is there any question? Yes, please.
Yeah, right. Actually, we modify shader, outline shader effects. So just sharp line is applied. So I don't know. It depends on sharp and curve. We modulate. We adapted different mathematic. Uh, uh, yeah, actually we write and also I will talk about this. I will talk later. Yeah, I will briefly talk about this detail after in this session. Yeah, yeah.
So one question. Yes.
Yeah. Hi, yeah. Impressive work. Yeah, thank you for your presentation. And my question is about the individual variability in the emotional ratings. In your research, we could see the ranges are the -2 to the +2 range.
Yeah.
If I remember correctly, the STEM scales that are the 1 to 9 points, right?
Yeah, right.
-4 to the 4. That means there's the individual variants that are within the objective rating data. So did you observe any the tendencies or let's say the average range that might be let's say harder to distinguish about the emotional ratings on your raw data? So could you please tell more detail about the emotion ratings raw data?
Okay. Sorry. I will show the measurement part slide. Uh, Actually, we use yeah, you say 1 to 9 SAM scale we use, and also rearrange it -4 to 4. Yeah. And also participant just write just rated yeah 1 to 9 scale. Yeah.
Yep. I think
Actually, nothing special,
I think it's
Madam.
time
Yeah,
to
I think-
time to move on to next
yeah, thank
presentation.
you.
So yeah.
So, hello everyone. Thank you for the presentation. So, okay, VR is this great medium that is able to deliver like highly immersive experience. And it usually does that, but using different senses. Like we have our sight with these stereoscopic images, high field of view. We also have our hearing, in which we usually find spatialized sound, so we can localize the sounds in the space. And we also have the ability to move around and explore the virtual reality environment as we will do in real life. So to get a unified and coherent perception, we usually need to perform these two steps. Like we first need to capture the sensory information, and then we need to process and integrate this information to achieve this unified and coherent perception of our environment. The problem is that these two steps are not always perfect, and some things can happen that will finally hinder the user experience. So in this work, we focus on two specific cases that might be wrong in these steps. So the first one is what we call a true spatial disparity. So in VR, sometimes we have a visual cue with an associated sound, but this sound sometimes present a spatial misalignment. This can happen because we have hardware problems or software problems because the spatial resolution of the audio is not great. And the thing is that if participants notice this misalignment, this will affect the final user experience. The second problem that we look into is that, okay, sometimes they're perfectly aligned, but we have found in a previous work that a perceptual spatial disparity can appear. This means that even if they're completely aligned, users perceive them as the sound coming from somewhere else, which is a problem if they notice, because this will affect the user experience. So in this work, we studied these two spatial audiovisual disparities. And okay, we're not the first one on doing this. This has been explored before, but they usually use simple and controlled environments. So you usually have a single audiovisual stimuli and a plain scene, which is great because you minimize all confounding factors and you also have a controlled environment. But the thing is that this is far from real applications. So if you think about the real application, we usually have this rich scene content. Participants are engaged in different tasks. We have a lot of stimuli, different audio sources, and also we have the people that are moving around the scene. So we cannot really assume that the findings found for this kind of environments can be extrapolated to real applications. So in this work, we not only look into these spatial audiovisual disparities, but we look into them by seeing what happens in more realistic VR experiences. So for that, let's start with the first one, the true spatial disparity. What we did is, okay, we built this baseline environment in which we have a simple task and a really simple environment like this. So we show participants this red ball that is producing a sound, and the sound can be completely aligned or present a different level of misalignment. So at the end of each trial, we ask participants, okay, did you perceive the sound of the ball coming from the right or from the left? And what we saw here is that if we are only presented with this red ball, their accuracy on the detecting misalignment is pretty great, also near the spatial resolution of the audio rendering. So this could be an issue for our real applications because participants or users are going to notice. But the thing is, if you think about these tasks, they are only focusing on this misalignment. And this is often not the case on a more realistic application. So we built this second experiment, which consists in a more richer scene. And we also ask participants to not only focus on the sound, but also to look for figurines like this one. So they explore the scene, looking for these figurines, and at the same time that they are exploring and looking for the figures, we saw then different audiovisual stimuli, in this case this bird and this clock, which are the ones that can have the audio completely aligned or presenting different misalignments. So at the end of each trial, again, we ask the participants if they perceive the sound to the left or to the right. What we saw here is that if before we had these thresholds, now they are much larger, which makes sense because now participants are engaging in another task and they cannot really pay attention to the misalignment. So we have seen that even if the sensitivity is really high in basic experiences, when we move forward to a more realistic application, the sensitivity is much lower. So maybe we don't need to care that much about these misalignments if they are sufficiently small. Now let's move to the other spatial disparity, in this case a perceptual one, and we focus on, for these perceptual disparities, in something that we've previously found in a previous work, which consists in, okay, if you have an audiovisual stimuli with their cues perfectly aligned, but participants are performing a rotation, they tend to overestimate the position of the sound toward the rotation direction, which is a problem because it also, this misalignment is related to the relative velocity between the head and the stimuli. And we saw that this can really hamper the final user experience. Although we studied this, a lot of questions remain open, because if you think of more realistic applications, what happens if you have more audiovisual stimuli? Because if you have more audiovisual stimuli in the scene, maybe you can use them as reference to, okay, this sound is to the left or to the right to this other sound. So this might not be that important. And a second question that remains open is, what happens if the participant is not moving? The disparity is still present, or it will disappear? So for the first one, we build this kind of application, which is an arcade game. But just to simplify the explanation, we had something like this. So we present participants with 4 different visual stimuli, and at each trial, one of them is producing a sound. So what we ask participants is to rotate their heads, and at the end of the rotation, they need to select the target that they think is producing the sound. So if we only do this, we observe that the sound was perceived as coming from the visual cue actually to the left of the actual target. So in this case, even if the green one is producing the sound, participants tend to perceive the orange one as the one producing the sound. And well, just to give you some numbers, but you have all the details on the paper, this happened 40% of the time, which is really critical. So in this work, what we did is, okay, what happens if we add these audiovisual cues that are highly identifiable in the scene? Participants can use them as reference point. So the answer is that their performance slightly improved, but the thing is that the disparity seems to be present, and they keep choosing the one to the right 35% of the time. So this problem seems not to be solved even in more realistic environments. So for the second question, what happens if participants are not moving? If the relative velocity only comes from the stimuli and not the head? Because we have seen that previous work highlight the importance of your own movement in perception. And for that, we again build this other application that is like a carnival row shooting game. But to simplify the explanation, same setup as before. We have 4 visual targets. One of them will produce a sound. But now the targets are the one moving, and we ask participants to remain completely still. So what happened here is that the disparity seems to completely disappear. Like, we could not observe this disparity, and they correctly choose the green one as producing the sound. So we can prevent this disparity in a way to preventing participants to move their head, but we need to be careful with this, because if you restrict the movement of participants, you are going to limit the engagement and the immersion. So just to summarize everything, we have analyzed these 2 audiovisual disparities, and we do that, but moving forward to more realistic applications, we investigate this true audiovisual disparity that seems to be not that important, or maybe negligible if you have an application in which participants are really involved and with rich content. We also have this perceptual audiovisual disparity that seems to be present even if you have more complex environment, and you can try to mitigate it, but by preventing participants to rotate their head when they're trying to localize an audio, but you have to be careful. And okay, just for future work, we will really need to increase the number and diversity of participants, which is always a limitation. And we also want to further explore this technique of adding audiovisual stimuli, because we only test two positions, but maybe having more or other configurations of the audiovisual stimuli could improve sound localization. And also we would like to move forward and explore other kind of perceptual audiovisual disparities. So thank you all for listening to me, and if you have any questions.
Yep. Any question? Yep. See the one hand there.
Thank you. This is cool stuff. I have a question about the environment. You said that the environment was more complex. I could see it was visually more complex, but do you also have an environment model that's affecting the propagation of sound, absorbing it and reflecting it in those more complex environments?
Yeah, well, we moved toward to more complex environments, but of course we did not test everything. We only rendered direct sound. We don't have these bounces
Okay.
of
So
sound.
your more visually complex environment was
Yeah.
not more complex in terms of how sound was transported.
Exactly, it's more
Okay.
visually complex, and actually they have more movement. For instance, in the arcade game, they are taking the arrows, they are fighting the arrows. Yeah.
Okay, thank you.
I saw another hand over there.
Hi, thank you. Interesting talk. I had a question about the last two experiments on the perceptual misalignment. So in the first one, I understand that people rotated their heads and the targets were stationary. And the second one, the targets were moving and the head was stationary. Was the relative movement the same in the two cases? So in other words, when I rotate my head, the targets are moving relative to me in a circle, basically. And it looked like in the video with the shooting gallery that maybe the targets were moving in a linear path. Is that the case, or were they also moving circularly relative to the head?
That's a great question. They are also moving circularly. And for the velocity, we can control the velocity of the target. So we set up 50, but it's true that we cannot really control the velocity in which you rotate your head. What we did is like, we allow participants to freely rotate, but if they were moving slower to that velocity, we just remove the trial and a scene appear like you were too slow, and the same for a higher threshold. We told them like you were too fast. So some people spend a lot of time trying to accommodate to that those threshold of velocity, but we try to keep them as closer as we could. Of course, you have more variability if the participants are moving. Yeah.
Thank you.
One quick question. I don't know. Yeah, maybe front, right? Yep.
Ability to discriminate where audio is coming from is dependent on spatial frequency of the sample and on the amplitude of the audio signal. Can you make any statements about how that might have affected that you always use the same samples at the same loudness levels with roughly the same frequencies, or has it changed between the experimental conditions?
Yeah, we try to use sounds that are in the whole frequency band. Like, for instance, for the red ball is like a white noise in the whole band. For the other sounds, to be realistic is more challenging, but we try to use the same level and more or less the same frequency. Actually, we only use this longitudinal difference of the sound, so it's easier to recognize the localization for the amplitude. We are not using vertical misalignments. So, but yeah, of course, that's a limitation.
I think we have a time limit. So, okay, let's give another applause for the presenter.
Good afternoon, everyone. My name is Mehak, and I'm an undergraduate student at the University of Calgary. And today I'll be presenting When Senses Collide, Investigating Modality Congruence and Interference Between Task and Notification in Augmented Reality. To start off with, I just want to tell you what I mean by modality in this case. So this basically means a particular mode in which something is expressed. So in this case, it would be either visual, audio, or haptic. And to start off with, I want you to imagine that you're waiting for a really important notification. And in scenario 1, let's say you're at a really busy airport and you're wearing layers and layers of clothes because you don't want your luggage to be overweight, and you're running around trying to find your terminal. Which notification modality would you prefer for that really important notification? Personally, I would not want it to be a haptic notification because with all that running and all those layers of clothing, I would easily miss it. I would either want a visual notification that I would regularly be checking my phone for, or a loud audio that would alert me about the notification. And in the second scenario, let's imagine you're presenting at an international conference. Oh, yikes. I would hate if a Teams notification popped up with that obnoxious sound and alerted everybody about it. Instead, I would just want a silent vibration in my pocket that only I would know about. So what I wanted to bring to light with these scenarios is that notification modality preference depends highly on the task at hand. And this was a research gap we found. So there's a lot of studies that study like different notifications in isolation. So we wanted to understand more about cross-model interactions in AR. So do congruent modalities help or hurt the task? We also wanted to find out how different notification modalities could support spatial and directional guidance in augmented reality environments. The main research questions that we wanted to answer was number one, how does the modality of a directional notification affect the user performance and perception independently of the primary task? And how does the combination of task and notification modality impact task accuracy, preference, ease of use, and task load? So to answer these questions, we came up with a 3x3 within subject study design. We had a total of 36 participants, and how the study worked was that the users would be performing a primary task, and the primary task was basically a Morse code pattern. So we would give them like one Morse code pattern to identify, and if it was the correct pattern, they would hit a button, and if it was the incorrect pattern, they would hit a different button. They were also surrounded by virtual buttons around them. And once they got a notification, again, in one of three modalities, so like a dynamic arrow, they would be guided towards one of the virtual buttons, or they would hear a spatial audio from one of the buttons, or with the haptic vest that they were wearing, they would be directed towards one of the buttons. They would just pause the Morse codes and attend to the notification and then come back to the primary task. And this is kind of what it overall looked like. So we had a monitor for the visual task, a speaker for the audio task, Xbox controller for the tactile task, it would just vibrate, HoloLens for visual and audio notifications, and the vest for the tactile notifications. For the hypotheses, for visual notifications, we hypothesized that overall, compared to the other modalities, they would just have a higher task performance and higher subjective ratings in ease of use and preference. For audio notifications, we hypothesized that it would reduce primary task accuracy as well as increase task load, especially when the task modality, like the Morse code modality, was also audio. For tactile notifications, we hypothesized that this would kind of be the middle ground, so more preferred than audio but less so than visual, and similarly for the performance. And lastly, for the cross-modality mismatch, we hypothesized that they would yield better notification response accuracy and result in an overall lower cognitive load. And moving on to what we found out. So for visual notifications, like we kind of hypothesized, they were faster than audio notifications to be perceived. And what I mean by perceived is that they were faster to be noticed by the user when they appeared. It was the same for tactile notifications, so audio overall just took the longest to be perceived. Similarly, for reaction time, audio took the longest time, whereas visual and tactile kind of took the least amount of time to be reacted to. And over here, reaction time basically means how long it took them to identify the correct directional button and hit it. In terms of accuracy, visual outperformed both of the other modalities, with tactile being the middle ground. And ease of use and preference as well, visual was the most preferred and easiest to use, audio least so. Visual notifications also demanded the least out of the user. So in terms of mental, physical, and temporal demand, visual notifications did not demand that much, and audio demanded the most. Moving on to audio, as mentioned earlier, they took the longest time to be perceived, to be reacted to, and the notification accuracy was also the worst in this case. They also took the most effort out of the users and caused the most frustration. But these results kind of set it up to be that the audio notifications were the absolute worst, whereas visual were really the best. However, if we look at the notification miss rate, users were more prone to missing the visual notifications compared to the audio notifications. And lastly, for the tactile notifications, like mentioned earlier, they were the middle ground. Users thought they were easier to use than audio, but less so than visual, and similar for the preference. In terms of performance, again, it was the middle ground. And lastly, for the cross-model mismatch, it often did reduce the cognitive load, especially when the notifications were tactile and the task was non-tactile. However, performance gains were not always guaranteed. Visual-visual pairing still gave the highest accuracy. Turns out humans indeed are visual creatures. We did have some limitations. It was hard to perfectly match like the primary task because even though it was all just Morse code, the perceived difficulty isn't really the same across. As well as individual differences, which was mentioned in the earlier papers as well, because the shape of your ear canal kind of changes the way you perceive spatial sound, so that might have caused some differences. One of the other limitations was that users reported fatigue over time from the haptic vest. Like, I think the burden of looking like a science fiction hero indeed is a heavy one. For future work, we would like to test in a more dynamic and real-world scenario that's more relevant to daily life and improve the haptic gear so that it's lighter but still provides that directional sense. And the key takeaway is that adaptive AR systems need to adjust notification modality based on the context of the task as well as the user state and preference. Yeah, thank you.
Thank you very much. Well, we have a lot of time for question and answer. So, yeah, we saw.
Thank you. That was such a great talk. You're a great speaker. I'm wondering about like if you're thinking in future work about interactions between these modalities, because if I think about it, I really love having my watch on my wrist because I get a notification that I should look at my phone, and I'm old and I don't always have my phone out. So it'd be really cool to see in the future if like interactions between these modalities might make people even better, because that's kind of more like what our everyday tasks are in terms of notification.
Yeah, no, I definitely agree with that. There have been studies where there were like actually like visual and audio together. So that's definitely something we look towards. Thank you for the comment.
Any further question? Yep, there's a hands.
Yes, definitely. So if again, like with the previous comment, if we combine like the notification modalities themselves, the task would also have to be like more complex to kind of, see, because real world, you can't really isolate all these modalities, right? Like it's not going to be a Morse code that's just visual, just audio, or just haptic. So that's definitely something worth looking into, and we'll be doing that. Yeah, thank you. Right now, I would like to bring up the previous paper again, like with the archery thing, where they were trying to identify like where the sound was coming from. Some like a gamified experience like that could definitely be one of the possibilities that we could bring up, because that's two modalities, right? Like you're visually looking at the like the targets as well as trying to identify where the sound is coming from. So yeah, something like that. Yeah, yeah.
Okay. Oh, one more hands. Yes.
Hi, incredible talk, really well delivered. One of your previous slides mentioned the like audio notifications were perceived slower than those of the visual ones. Previous reaction time literature kind of like says audio is perceived quicker. Do you think it's because you're possibly like it takes more cognitive effort to spatially locate these?
You got it. That's
Okay,
definitely it.
great. I
Like,
must
yeah.
have missed
Yeah,
that in
go
the
ahead.
talk, but thank you.
No, I didn't mention it, but like from the user interviews that we had, we found out that even though it like gave them like a sense of emergency, like the audio notifications, just the fact that they had to directionally also kind of pay attention caused it to be a delayed reaction towards it.
Great, thank
Yeah.
you so much.
Yeah.
What kind of HRTF data you use?
I'm sorry?
What kind of audio engine you use for? So spatial, rendering of the sound.
yeah.
You
S-
probably use the HRTF, right?
Yeah,
Like
yeah.
previous
Yeah,
presentation.
like with the HoloLens, like the
Yeah.
inbuilt, yeah.
So you
spatial
use the
features.
built-in
Yeah, yeah,
HRTF
yeah.
data set. Okay, maybe that is the reason why.
Yeah.
Yeah.
Although I would like to mention that we had a couple users that were really into video gaming, and they had the best scores for audio notifications. They got them all accurately, and they preferred them the most too. So I would say it depends on like past experiences of the user as well. So yeah.
I hope that there's no person from Meta here, but HoloLens HRTF is not so great. Anyway, that's my personal comment. Okay. Any further question? Oh, so yeah, let's give another person.
Just related to the HRTF and those localization stuff, was it played over headphones? Was it played over speaker? And how they're
So
listening to
just
sound?
the HoloLens speaker. So like the task itself was an external speaker, like the Morse code, but the notifications were the built-in speakers on the HoloLens.
Also, it was not over headphones or anything
No,
like
no
that.
headphones.
All right.
Yeah.
Yeah, sure, why not?
Okay. Hi again.
Yeah.
So, did you experience any reversals? So the phenomenon of having a sound in front of you also be perceived as directly behind you, or anything like that? And same thing goes going in this vertical axis as well. I know you didn't do the vertical axis, but it's kind of interesting.
Yeah,
to think about.
like there were definitely cases where the users completely could not understand where the sound was coming from. And yeah, like you mentioned reversals, there were some where the direction itself would be like northwest, let's say, but they would go to south or something. So yeah, again, like the way we perceive spatial audio is one of the limitations that we had in this paper. So.
Oh, okay, yeah, totally. Thank you so much.
Yeah.
Okay, if there is no further question, let's give another applause for the presenter.
Thank you.
I think that's it. So have a wonderful other sessions and presentations and demos. Yep.